Can you see my screen?
Yes, Prof. We
Okay.
can see
Okay.
yours clearly.
Then I think I can start. So we want to discuss a little bit on how computational materials design can help to promote the development of high performance batteries. So why do we need to do that? So we need safer and higher energy density batteries, and higher energy density will in principle make batteries more dangerous. So we have all seen such fires on when you just build a new fleet of electric buses. So this was in a small town in China. A few minutes later, it looked like this, and then like this. So of course, this should be avoided, and it's not only in China. So this one is in Germany, same thing at smaller scale. So we need safer batteries. At the same time, we cannot compromise on the energy density. We even want to have higher energy density. We want to charge the battery fast, but it should be abuse tolerant. It should contain sustainable materials. So you have heard, I think, yesterday and earlier today, that we need to have less cobalt and replace it by nickel and manganese at least, and we will see more of these materials developments here. And one advantage of solid state batteries is also, there's no leakage. So you can just stack these individual batteries. You don't have to wrap each one into a casing. And that also saves a lot of weight. And when you go from lithium ion, from the graphite batteries, to lithium metal batteries and incorporate this, then the target is 500 watt-hour per kg. So this is, you see, can ask whichever country you want. So US, of course, claims to reach that very fast, but they haven't been there. Japan, China, Korea, all kind of agree on it may take until 2030 to reach this. And on the way, you see all these NCM mixtures improve, but at some point, you have to go to lithium metal anodes and you have to go to solid state to reach this goal. Why don't we have that now? Because there are quite a number of challenges to be overcome. We will look into some of them now. When you increase when you replace the liquid electrolyte by solid electrolyte, in our lab, we make ceramic pellets, but they are much too thick. We have to make things that are at least as thin as the current separator layers are. So it's 500 micrometer, you will never get beyond 100 watt-hour per kg. So we have to go below this 30 micrometer or below 25 micrometer to have a chance to get to the 500 watt-hour per kg. And that's a bit challenging to do with ceramic pellets. So in the end, we will quite often have to use polymer ceramic composites. On the other hand, if we anyway have to be so thin so that we don't need too much volume in the battery, then it's no longer as challenging to reach the conductivity, because in the thin layers, the absolute resistance will be small, even with somewhat less conductive materials. And when you look at the solid electrolytes, there's different classes of materials. Each one has its own problems. The oxides are relatively stable, but it's difficult to densify them so that the total conductivity, including the grain boundary contributions, is high enough. For the sulfide-based materials, the reaction with water is a main problem for many of them. We will look into that too. And for the halide solid electrolytes, it's also still the bulk conductivity not high enough, and they are also corrosive. They are better on the cathode side, maybe not so good on the anode side. So we may have mixture of different solid electrolytes in the end. When you want to optimize your sulfide-based solid electrolytes, then yeah, it should be light so that it doesn't harm the energy density too much, but at the same time, it should not react with water too much. And see, in this axis, the vulnerability to hydration, so from very bad to much better, change here from red to green, and the heavier atoms in terms of mass per mobile lithium are also here red, the lighter ones green. And you see in terms of this mass, the phosphorus is near ideal. That's why many of the materials now in the lab are based on phosphorus, on thiophosphates. But for practical application, you cannot build your own fab completely into a glove box. You have to at least allow a somewhat higher water vapor pressure. So you have to go in this direction. So these are the more realistic candidates for practical use. So one of them is silicon-based materials, and recently the Kano group has come up with this material, and we then try to explain why it works. So the phosphorus doping they use is not so much to enhance the conductivity. So, but this material is a metastable material, so it's different phases. Some phase is highly conductive, but the equilibrium phase is not so conductive. So, and what the phosphorus actually does is to stabilize the metastable, highly conductive phase. We also looked into going to materials that are much less vulnerable to water. So if you have antimony or tin instead of phosphorus, then you can even drop the material into water, recrystallize it from water. But at the same time, it's a little bit heavier. So that's, for example, here we have the Na3-SBS4, so where the antimony is replacing the phosphorus. Then we can make nice battery, very good sodium conductor. So we treat lithium and sodium, so very, very similar. So that's, you will see some results for lithium conductors, some results for sodium conductors. And then because we can work in water, very easy to do some doping, because we just throw the dopant into the solution, and when it crystallizes, you have some of the dopant also in the material. And with that, we get material with higher conductivity by the bromine doping in this case, and you have material with better interfacial properties. Because the material fails at the anode, but it fails in a way to produce sodium bromide, and that forms a kind of stable, very thin layer, not too high resistance, and with that, then the overpotential remains very stable. Without the doping, you see it slowly decomposes, and the overpotential becomes higher and higher. Okay, when we want to address the thickness of the ceramic pellets, then we have to really go to thinner and thinner materials. We can use classical tape casting when mixed with the solid electrolyte with some polymer phases, but we have to make sure that the polymers that we choose are those that bonds very strongly to the ceramic phase. So that's a bit the trick with that. And then we can make materials that are flexible, can make rather large systems, and we use that for our lithium air batteries. So by photopolymerization, we can make even thinner materials. So these here have high ceramic loading, therefore higher conductivity. So that's just mentioning the lithium air batteries, and we can use them in, so they even work better when we have higher, slightly higher temperature, maybe 50 degrees, and we can easily get that from low-grade waste heat from industry. And then we can use that to have 99% efficiency. So energy efficiency, not only Coulombic efficiency, but really energy efficiency in these batteries. Okay, but spin coating is very cheap, easy technology. For that, our composites have to be a bit softer, so more fluid, and that means the ceramic content in these materials is a bit lower, but still it's very important to enhance the conductivity of these polymeric conductors. So we see here that's directly coated onto the lithium. So you have a lithium layer, and then you can, by spin coating, directly produce a very thin solid electrolyte. On this, you optimize the mass fraction of the ceramic to get the highest conductivity. And so it's a bit difficult to read if you're not used to this scale. So this here is room temperature. So this is a pure polymer below the glass transition, has low conductivity. If you use the ceramic, has much higher conductivity even at room temperature. In the high temperature phase, the difference between the ceramic containing and the pure polymer is not so big, but of course we want to operate our batteries close to room temperature, and that's very helpful. So we can use the LFP batteries, rather stable for such a solid electrolyte batteries. We can also get to relatively high loading, so that's very important. You can always get nice performance in the batteries if you use very little cathode material only, but for practical use you need rather thick cathode layers, and then we need to optimize the transport of the ions and of the electrons in this cathode layer. Okay, we have a rather easy tool that everybody can download. Actually, it's meant for academic use. It's free. For industrial use, we have a $99 fee for users, but yeah, no control. So we can just load the crystal structure and then analyze it very easily on your laptop. You can see what are the migration barriers, so that translates into the activation energy for the transport, how much faster transport becomes when you go to higher temperature. You can see where in the crystal structure the ions can move. You can predict which dopant would work for this material. It's very simple, very tool that can run on any Windows laptop, and still the accuracy is comparable to what you can do with DFT simulations on on supercomputers, and it is much faster. So this is within one CPU hour you can handle 5,000 different compounds, more than you probably want to consider. So you get these pathways, you get the migration barriers. You can use that to predict new materials. So this was a material developed by the Kano group in Japan. They're good lithium conductors, and then we thought, how do we have to design this material to make a good sodium conductor? So we found that you have to change the ratio of these ions a little bit, and then you get this phase, and that is actually at that time was the fastest sodium conducting material. Now it's no longer. So the Na3SBS4 and Na3SBSE4 are faster, but we can use that to make all solid state room temperature. If you're not interested in solid state batteries, still you can utilize this method, because it also gives a way to compare the rate capability. How fast can you charge and discharge a battery without losing capacity? So always when you change the rate, here C rate means, here you see 2 means you charge and discharge within half an hour, 0.2 means you charge and discharge within 5 hours. So that inverse scale. So, and if you charge faster, then the capacity that you can get out will at some point drop. but how much it drops depends on the ionic conductivity in this material. So when you have this pathway analysis, you can predict how these curves look like, at which point is this decay and how steep is the decay. And we, for example, lithium iron phosphate, very famous lithium conductor, sodium iron phosphate, very poor material in the crystalline state, so very low rate capability. But when you go to amorphous phase, much better phase. So, and such studies are relatively easy with this approach. When we want to find better solid electrolytes, we can also look at rather generic guidelines. So when we here look at all different oxides, we said we want to stay in the oxide range for higher stability. Then you can compare how good a glass former would this particular oxide will be. Very traditional approach. So you can classify the materials and be good glass formers, conditional glass formers, or network modifiers that destroy the network that is formed here in these glass formers. And then when you compare that with some known good lithium conductors, you will see many of them are in this upper range here of boundary between conditional glass formers and glass formers. And there's a reason for that. So because the same factors, low coordination number, high charge cations, building stable blocks that have free space around them to move around, that's really also the same thing that also helps ionic conductivity. So we can use that then to design new materials. For example, we will look a minute into lithium tantalum phosphate as one such new material. We can also look at across many mobile ions, what is generally what helps the ion transport. So here, the migration barrier would increase, so transport would become worse and worse if you have a high coordination number, if you have high charges. So that's why monovalent ions like lithium, sodium are always the best choice. Also, the anion charge shouldn't be too high. The size ratio, so the cations shouldn't be too big compared to the anion size. The melting point should be low of the material, and the material should be not too ionic. So it's actually helpful if the ion is, if the salt is not really a salt. So it's somewhere between a salt and a covalent compound. So we said LiTA2PO8 is one of such material that follows the guidelines like this glass forming materials. And so we can predict in different ways the pathways. We can study in detail. We can see how with different temperature the materials. But I think that's more to see why different methods find different results. So near room temperature, it's a 3-dimensional conductor. Ab initio molecular dynamics simulations claim it's a 1-dimensional conductor, but they have to be conducted at very high temperature. And you can, when you study this, you can see that with increasing temperature, the material goes from 3-dimensional near room temperature to 1-dimensional conductor at a very high temperature. So the barrier for 1-dimensional transport goes down when you increase the temperature. The barrier for the 3-dimensional transport goes up when you increase the temperature. Okay, then when you practically want to make the material, we said for oxides, you always have to worry about grain boundaries. So you have to find the best sintering, either here by conventional sintering. We also explore spark plasma sintering. There you can really make rather dense materials. You get very 99% dense materials. Conductivity, so still comparable with both methods. And that has a reason, because with spark plasma sintering, much faster. So within a few minutes, your sintering is done, compared to here 10 hours with this conventional sintering. But the grain growth is different. So with the spark plasma sintering, you have in the end a dense material, but a dense material consisting of rather small crystallites, and that also leads to slightly higher resistance. So you can make materials, make the battery of this material, so you can test, is it stable with lithium? No, it is not. So gradually resistance increases. So you have to do something about this. On the cathode side, everything's stable. So this material combination is stable. So that's fine. So on the anode side, so we have then introduced this, just a few drops of a liquid electrolyte to separate them, and then you can get decent cycling of this material. And when the cycling, so when the separation doesn't work so well, also not catastrophic, because here in the initial cycles you get the what you expect from a lithium to lithium iron phosphate battery, but then it seems the lithium contacted the LTPO, the solid electrolyte, and led to some decomposition, but the battery doesn't fail. It just converts into a different battery. Now your practical anode is a kind of partially reduced LTPO, and that can be run very easy. So with that, you can really make a battery that you don't need any glove box. So this battery can really be made in the open. So you mix LFP, then you have a layer of this LTPO, all stable in the environment, and then have steel electrodes or copper electrodes, so that you create the lithium only when you discharge the LFP or when you charge the LFP, and then this can be run without any special equipment. When we want to make high performance materials, of course, we need to again make it very thin. Again, we use the polymer composites to make these. Then we can make them into, for example, here lithium sulfur batteries with many cycles. Maybe we skip a number of things here. So we can also use our methods to screen what kind of amorphous materials can be used for cathode materials. In order to reach this 500 watt-hour per kg, you practically need an cathode material that can reach 1000 watt-hour per kg if you just count the cathode material. So that means you have to have here like 300-400 milliampere hour per gram, and then 3 or 4 volt as the voltage of this, then you can reach this. So we try to find in the corresponding systems here with the glass formers to have high ionic conductivity, where would be good materials, and then we can maybe skip all this.
Because we have a time constraint.
I come to the end. So just
thank you so much.
We have the dopant predictor also built in, where you can let the program tell you which material should you dope in to which one would dissolve. And then last point is always we want to not only find the migration barrier, so we want to know the absolute conductivities, and the recent version of the material of the soft PV software now also has an absolute predictor. So you just give the compound, run this energy landscape calculation. That means press one button and then you press the next button. It will tell you what is the conductivity you can expect, and then you can also modify. If you add a dopant, then how would it change the number of ions and the number of sites in the system, and then you can see what to expect from a certain dopant. Maybe skip all this and then come to the end, and thank you for the attention, and thank the people here for having done the work. And you may recognize one of the persons. So Joe Yongkai, you have maybe seen yesterday. So he was my very first PhD student here in Singapore. And thank you for your attention.